So in this video, we will visit some of the perhaps the most important rules of probability, and we will kind of trying to derive them experiment. This experiment involves two urns or containers, you want to call it. Okay, so this is the two containers. I will call this container 0 and container 1. And these containers, they have inside some widgets, balls, or whatever. I will use these symbols for, they have 6 of these widgets, and 2 of those widgets is container 0. And container 1 has this widget and 3 of those. Okay, 2 types of widgets. Okay, so can so the experiment goes as follows. Okay, so this is the experiment. The first stage of the experiment involves to pick randomly a container or urn. And the second part of the experiment is, after you selected the container, you pick, you sample one of those widgets out of that container. You select, you sample, not select, so you sample an object widget out of this container with replacement. Okay, so this with replacement, what is really the meaning of the with replacement? With replacement means that after you sample an object, you put your hand inside, you pick an object out of this container you have selected in step 1. You look at it, you determine what it is, you write it down that I sampled object the white or black, and you put it back inside the container. That is with replacement. You are effectively replacing this object back into the container. So we will call this random, the container, we will denote it with a variable y. And we know that the y could be, because we have only 2 containers, could be either 0 or 1. Also, x is the letter we will choose to denote the widget. And we have 2 types of widgets, the white widget and the black widget. So, we could actually say, okay, this is 1, this is 0, whatever, it doesn't really matter. So we cannot really do calculations with this kind of symbols over there, although potentially we could, but we replace them with 1 and 0 equivalently. Okay, so that's basically the x and y, both are effectively binary in this specific experiment of ours. So let's assume now that someone actually gave you a probability distribution of y. And because y is discrete, obviously you would expect to see some discrete probability distribution. Let's assume that probability of selecting the container 0 is 40%, and the probability of selecting container 1 is 60%, obviously, because the sum, being a probability distribution, should be equal to 1.0. And ask you to plot the probability distribution for x. Okay, and I guess x also is discrete in this case, so it's 0 and 1. So obviously, without really, the only avenue to come up with this probability distribution for x is to run this experiment multiple times. So in this specific case, we will run the experiment, let's say, n times. So this thing here is executed n times, this process. Well, we have effectively a probability space that involves two variables, x here and y is here on this kind of axis. So this is for x is equal to 0 and 1, and correspondingly for y is equal to 0 and 1. Okay, and we are at any experiment round, we are getting one of those points. Obviously, this point, for example, corresponds to first selecting the urn 0 and then drawing out of this urn the object 0, which corresponds to the black widget. So if we count the number of events that falls one of those quadrants over here, we will, let's call them this, the number of events in this quadrant related to x and y. The first index will be what was the x, and the second index will have been will be the y. It's just a convention. The indexing is not necessarily important. 0, 1. In this case, it kind of makes sense to call them like this. And 0, 0 and 1, 0. And now we can actually start kind of quantifying what would actually be the probability distribution of x, because now we have the data in front of us. So the probability that x is 0 is given by summing these two events n0, 0 and n0, 1. So effectively it is really this area over here, irrespective of what urn was, of course, selected first. And so we can actually write that, I'm not sure exactly which one is larger, which one is smaller. I have not really counted, strictly speaking, the events here, but just want to write down the expressions n0, 0 plus n0, 1 divided by n. And the probability of x is equal to 1 is going to be this area over here, n 1, 0 plus n 1, 1 divided by n, where capital N was the number of times that we have executed this experiment over and over again. Now, what if someone asked us to quantify another probability distribution, which in this case is the conditional probability distribution of P of y given x? Well, this is a probability of selecting the urn given what we are actually observing after we pick an object out of it. So, I mean, obviously we can think about this probability distribution as having, if you like, 4 components, and it's not, of course, difficult to see that this is the probability of y is equal to 0 given x is equal to 0. Probability of y is equal to 1 given x is equal to 0. And then, of course, the corresponding probabilities for the other choice of the other choice of the other observation of the widget. Okay, so we have effectively 4 components, and I believe it's easy to start quantifying those components. What will be the probability of 0 given x is equal to 0? So first is this component, who actually would be the n0, 0 divided by, because x is always equal to 0, this will actually be the sum, just like we have done over here, 0, 0 plus n 0, 1. This component would actually be correspondingly 0, 1 divided by n 0, 0 plus n 0, 1. And now this component over here is going to be n 1, 0 divided by n10 plus n11. And similarly, this guy will be n11 divided by n10 plus n11. So this is fairly easy to see by just observing, if you like, this diagram over here, and writing down these relationships from the counters, or from the counts that we have seen. And as you probably already have noticed, already we have an ability to couple this type of two queries to the sum and product rules of probability. Because take, for example, the first query that we asked, what is the probability distribution of X? You can very clearly see here that in this specific case, we have a summation involved. And if you write down the sum rule, that sum rule was effectively the probability distribution of X is equal to the sum over Y of P of X comma Y. We are marginalizing out by summing over all possibilities of Y over the joint distribution. And this is exactly what we see here. We sum over all possibilities of X that we can actually get. With overall possibilities of Y we actually can get, and therefore we are obtaining the probability distribution of X. So this effectively is the same as the sum rule that we have tasked to start sort of not necessarily deriving, but that's just observing out of this kind of experiment. And so this is a very straightforward, if you like, rule that we can be derived out of this exercise we have just done. Now, this other rule, which is the product rule, takes a little bit more work, and that's what we will do next. So for the product rule, we'll start with this relationship over here, and we'll try to do a substitution which is obviously evident, and for that I need to use a different kind of pages. I run out of space here, so I'm just going to carry over, and what I just wrote here, P of Y given X, one of these four was the probability of Y is equal to 0 given X is equal to 0. This is one of those four components, which was actually given by n00 divided by n00 plus n01. Okay, so now we can actually try to understand what is really the n00, okay, from this relationship. So we can solve for n00. It's going to be P of Y is equal to 0 given X is equal to 0, n00 plus n01, and just leave it now like this without really proceeding any further. So now if we write the P of X is equal to 0, comma Y is equal to 0, then obviously, if you can recall from the previous kind of diagram, these are all the events that are in this quadrant divided by n, which is the number of experiments we have run. So this is basically n00 divided by n. And then we can actually replace n00 from here. It's going to be equal to P of Y is equal to 0 given X is equal to 0, n00 plus n01 divided by n. Well, look at this. This guy over here is exactly what we actually called the P is equal to X is equal to 0 probability. So effectively we can write this expression as P of Y is equal to 0 given X is equal to 0 times P of X is equal to 0 from this diagram over here. And so this is now something that starts to remind us, if you like, the product rule as an expression. And if we are to repeat the same exercise for the others, we will rapidly come to the conclusion. And this is the other expression. I was just writing it down. Y is equal to 1, given x is equal to 0, times p of x is equal to 0. And similarly for the others, x is equal to 1, comma y is equal to 0, p of y is equal to 0 given x is equal to 1, pi of x is equal to 1. And lastly, p of y is equal to 1, comma x is equal to 1. This is p of y is equal to 1, given x is equal to 1, times p of x is equal to 1. So we actually have shown that these expressions are true for any single possibility of x and y, and then we can safely conclude that in general, p of x comma y is equal p of y given x times p of x, which is the product rule. And of course, we now know that because of p of x comma y is equal to p of y comma x, we can actually write another version of this kind of product rule, which is p of y comma x is equal to p of x given y times p of y. And then if we take these two equations here, we come up with something which is very important and essential in everything that we will be discussing in Bayesian kind of learning, which is the base rule of p of y given x is equal to the p of x given y times p of y divided by p of x. And this is a very generic one, the very generic expression, direct consequence of the product rule, that we will be, and we can actually will now start giving semantics to x and y a bit in a different video.